Okay, so this is part 2 of lecture 12. Make sure you're watching in the right order. So we've covered speed, velocity, and accelerations. Newton gave us a definition for force, which is simply the mass times the acceleration. And that plays into his first of his 3 laws of motion. So Newton's first law of motion, this was actually discovered by Galileo, and it's called the law of inertia. And it states, an object remains at rest or continues moving in a straight line at constant speed. So if you're in a straight line, you're not turning. If your speed isn't changing, then your velocity is also constant. Constant speed in a straight line, constant velocity. No direction change, no speed change, no velocity change. So an object remains at rest or continues moving in a straight line at constant speed until an unbalanced force acts on it. Couple of fine points to point out here in the wording of this law. Being motionless at rest means that your velocity is 0 and you're going to stay with 0 velocity. You're not going to change that because that's an object remains at rest. It's not moving now. It won't be moving a second from now, 10 seconds from now, 15 seconds from now. As long as there's no unbalanced force acting on it, it will remain motionless. So being motionless at rest is just a special case of moving in a straight line. You're just moving in a straight line with a constant velocity, a constant speed of 0. Your speed never changes. So you could be moving at 10 meters per second in a straight line, and as long as there's no unbalanced force, you will continue to move at 10 meters per second in that direction, in that straight line. You could be moving at 5 meters per second in a straight line, and as long as there's no unbalanced force, you won't change. You could be moving at 1 meter per second in a straight line, and as long as there's no unbalanced force, you'll just continue to do that. You could be moving at 0 meters per second. If you're moving at 0 meters per second, the direction becomes irrelevant. You're not moving, so that you have no direction to your motion. But as long as you maintain that 0 velocity, it's the exact same situation as moving in a straight line at 10 meters per second, moving in a straight line at 5 meters per second, moving in a straight line at 1 meter per second, moving in a straight line at 0 meters per second. They're all just different scalings of the same motion. Constant speed, constant direction. So we really don't even need this remains at rest part. An object remains moving in a straight line at constant speed until an unbalanced force acts on it. But most physicists like to put the rest in there, at rest in there, so that it emphasizes that point. Things don't spontaneously start moving unless a force pushes on them. Common sense. A lot of Newton's laws are common sense. Newton just gave us a very rigorous mathematical way to describe and manipulate our common sense. And then the other words to draw our attention to in his first law are unbalanced forces. What's an unbalanced force? Well, if you have an unbalanced force, there must be a balanced force scenario. And so balanced forces are forces that cancel each other out and produce no net effect. So scenarios where something is being acted on by more than one force, but those forces are in opposite directions and equal in strength, so they push equally from both sides, they pull equally to opposite sides, and so they don't have a net effect. They cancel each other out. And so as an example of that, I can take the power cord from my laptop here, and I can hang it. I can take the transformer and hang it from the cord. And so right now, there are multiple forces acting on the transformer, the heavy part of the plug. Gravity is pulling it downwards. Here, let me coil up the cord so that it's out of the way. So there, gravity is pulling this straight down, but it's not moving. If I hold it still, it's just suspended there, motionless. So Newton's first law tells us, if this thing continues to remain motionless, there must not be any unbalanced force acting on it. It's being pulled down by gravity, so there's one force acting on it. The force of gravity is pulling it straight down, but the cord connecting the transformer to my hand is also exerting a force on the transformer. It's exerting a pull straight upwards. Gravity is exerting a pull straight downwards. The two poles are exactly equal and cancel each other to zero. So there's no net force on my transformer. It has no unbalanced forces acting on it. So it hangs there motionless. And it will continue to hang there motionless until the scenario changes. If I drop my hand, then the cable is no longer able to pull upwards with an equal strength equal to gravity. And so as I drop my hand, the transformer moves and drops until I stop moving my hand, and then it stops again. Tension in the cable balances gravity pulling downwards. The two things are balanced. And so a suspended object, like my transformer, whatever the cable is that's supporting your object, that balances gravity and you get no motion. If I have an unsuspended object, if I let go, once I let go, the cable is free to move, the cable is free to move, the transformer is free to move, there's nothing pulling upwards to balance gravity, so it immediately starts falling. As soon as this condition isn't met anymore, now there is an unbalanced force acting on the transformer, so it no longer remains at rest, moving in a straight line at constant speed. It had speed 0. The next second, it's got speed downwards of 9.8 meters per second. The next second after that, it's got a speed downwards of 19.6 meters per second. Every second that it falls, it's going to gain 9.8 meters per second in velocity, be accelerated due to gravity. And so an unsuspended object means that gravity is unbalanced and the object falls. And so another way to think of this wording, another way to, an equivalent sentence, another meaning to Newton's first law of motion is that an unbalanced force will change the speed, change the direction, or change both of an object. And so unbalanced forces create accelerations. They are the root cause of accelerations. If you see an acceleration, there is an unbalanced force present. If there is an unbalanced force present, there will be an acceleration. These two are inevitable. You cannot avoid it. If you have one, you must have the other. Forces and accelerations are two sides of the same coin. You get one, you're going to get the other, without question. Get in there. All right, so, and Newton's first law also tells us that if something is moving in a straight line, it will continue to move in a straight line unless there's an unbalanced force acting on it. And so I'm going to try to demonstrate this for you with okay, so now you can see the tabletop here in the video. I have a steel ball bearing here, and I'm going to set it so that it's motionless on the table. And so there it is. just sitting there motionless. There are forces acting on it. Gravity is pulling it downwards, but the solid, rigid table is in the way. So there is no choice. It's not moving, so there can't be unbalanced forces acting on it. Something must be balancing gravity. It's the table itself. The table is generating an upward push on the ball, and that upward push is exactly equal to the downward pull of gravity, such that the two vectors have the same length but opposite directions, so they cancel each other to zero. With zero forces acting on the ball, it continues in its current state of motion. Its current state of motion is not moving at all, so it continues to not move at all. If I let the ball roll across the table, so there's my tabletop. Make sure I'm still in the video. There's my ball on the table. Gravity is pulling the ball downwards. The table is pushing the ball upwards. The two forces are exactly equal. But this doesn't require my ball to be motionless. If I let the ball move with a rolling velocity v across the table, at every point where it's touching the table, as the ball is rolling, it'll be here later, it'll be here a little bit later, it'll be here a little bit later than that. At all times, there's a point of contact with the table. Gravity is trying to pull it through the table. The table says, no, I'm rigid, I'm solid, you're not going to fall through me. And so it just constantly keeps that gravitational force balanced. So as the ball is rolling along, all the forces are balanced on it. And so it will just continue to roll in a straight line in the same direction that it starts. So if I tap this ball and set it rolling, it just rolls across the table at constant speed. Just rolls across the table at constant speed in a straight line until something happens to it. I grab it, I stop it, it falls off the table. Once the ball reaches the edge of the table and rolls off it, now there's nothing balancing gravity. It will accelerate downwards and fall to the floor. Common sense, carefully codified with math. And so once Newton realized that this was true, Galileo had already discovered this, Newton thought through the implications of it, and he realized that balls roll in straight lines unless a sideways force acts on them. If the table is tilted, then there's a little bit of gravity pulling it sideways, down the slope. And so a tilted table, something will move in a curved path. But on a perfectly flat table, things will just move in straight lines. And so straight line motion is what things want to do. It is the natural state of motion in our universe. Anything that isn't moving wants to remain motionless. Anything that is currently moving wants to continue that motion in a straight line at a constant speed and will continue to do so until an unbalanced force changes the scenario. So straight line motion is the most natural state of motion. And so Newton realized then that circular and elliptical motions are not straight lines, and so they require an unbalanced radially inward force. As we saw in the earlier segment, a car turning at constant speed has to be accelerated sideways. Forces and accelerations are the same thing, two sides of the same coin. If there's a sideways acceleration, there has to be a sideways force. And so Newton realized that circular and elliptical motions, the motions of the planets in their orbits around the sun, the motion of the moon in its orbit around the earth, that these were circular paths, curved paths, elliptical paths, and curved paths require unbalanced radially inward force. There has to be a force pulling you towards the inner edge of the curve in order to in order to make the object move in a curved path. And so on this slide here, we're imagining the following scenario. So I'm going to play with my transformer again. I've got my transformer. It's attached to a cable. So I've got a mass at the end of a string, the end of a cable, and I'm going to spin it over my head. And so the transformer is moving in a perfect circle around my fingertips. Right? So it's just moving in a perfect circle. If I do it vertically, then the white transformer is moving in a circular path around my thumb. So the thumb is the center of its orbit, and it's moving in an orbit. You can imagine my fist is the sun, and the transformer is the earth. I don't know why the damn video camera isn't tracking me. So there we go. The white transformer is the earth circling the sun. The white transformer could be the moon circling the earth. But it's circling. And so if we look at this scenario from above, here I have a student holding a mass, a green ball, tied to a string. He's holding onto the string. He's spinning it over his head like I was just doing. The diagram has a red arrow representing the current instantaneous velocity of the ball. In this case, on the coordinate system, on the plane of the screen here, at this moment the ball is moving down the screen. It's over his head, but so the red arrow points downwards. But as the ball moves to new positions, the arrow is going to change its direction. So right there's my red arrow for my current velocity. The only force that's turning it is the string pulling inwards towards my hand. The string can only pull. The string can't push on the ball. It's a string. It's floppy. It's flexible. It's loose. The only thing pulling on my transformer as I spin it is the tension in the cable, and that pulls the transformer inwards. So there's my force, there's my acceleration, and it's pointing inwards. So I'm going to take this, I'm going to move it down to the tip of my red arrow, and it's going to turn my red arrow without increasing its length or decreasing its length. It's perpendicular to the ball's current motion. The motion is down the page. The acceleration is inwards towards the thumb, which is to the right on the page. They're 90 degrees perpendicular. The speed of the ball isn't going to change, but the direction of motion is going to change. And so after a quarter of a turn, just constantly pulling it, always pulling it inwards towards the center, it'll have turned to here. It'll be moving at the same speed, but now it's moving to the right, and the pull is upwards, 90 degrees perpendicular to it. And so it will turn more. And once it gets a half a circuit around, it will be pulled inwards, moving upwards, 90 degrees perpendicular to each other. So it'll just continue to turn more and end up at the top being pulled downwards, moving to the left, being pulled downwards. And so at every point in the circuit around here, in this circular orbit, the current velocity is tangent to the orbit, and the acceleration is radially inwards. They're perpendicular to each other, so the speed doesn't change, just the direction changes. And so when you string a ball on a string, the string exerts a force that pulls the ball inwards. It moves in a circular path. You're playing tetherball. However, so Newton realized this. In order to make the moon orbit the Earth, in order to make the Earth orbit the sun, there has to be a pull, an unbalanced force, and that pull has to be pulling the orbiting object towards the center of the orbit. Not surprisingly, where the bigger, more massive object that it's orbiting is located. And so Newton also realized that if the string were to break, so right at this moment, right at this instant here, the string breaks, then the acceleration inwards is going to disappear, and when that happens, his first law is going to take over. The ball no longer has an unbalanced force on it. It's just going to sail straight forward in the same direction that it was going. It's going to fall due to gravity, because there's an unbalanced gravitational force on it now. While the ball was swinging around here on the string, it wasn't in a perfectly flat plane. It was sagging a little bit so that the tension of the string both pulled it inwards and upwards just a little bit to balance gravity so that it could continue to circle, 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 circle without falling to the ground. Gravity was balanced, but the inward pull created an unbalanced force, and so once the inward pull disappears, the force making it turn in the circular path disappears, so it's going to move in a straight line down the page, but it's also going to fall to the ground because the lifting force that was previously helping to counter gravity has disappeared. So Newton realized that orbits, which are curved paths, ellipses, require radially inward pulls. There's no way around it. Something's going to turn, it's got to be shoved sideways, pulled sideways. And orbits are curves. So something's got to be pulling the orbiting object sideways to make it move in a curve. All right, so then we get to Newton's second law of motion, which is a long sentence, but it turns into a short equation. If an unbalanced force, let's symbolize that with an F, acts on a mass, let's symbolize that with an M. That unbalanced force acting on the mass is going to cause an acceleration, symbolize that with a lowercase a. And that acceleration is going to be directly proportional to the force and inversely proportional to the mass. So in algebra, I can write it this way, F equals ma. It's a nice, simple way to write it. Force is equal to mass times acceleration. Or the way the sentence is written, acceleration is directly proportional to force and inversely proportional to mass. So it fulfills the conditions of that sentence. And when you use metric units, kilograms for mass, meters per second for acceleration, meters per second squared for acceleration, kilograms for mass, then the force is in units of newtons, and there are no constants in this equation. In that set of units, the constant is 1, a unitless 1. So it's a really simple equation. I think this is the best way to remember it. Acceleration is directly proportional to force and inversely proportional to mass. If I make the force bigger, the acceleration will get bigger. If I make the mass larger but keep the force the same, I'm going to get less acceleration. And so forces, accelerations, and velocities always include directions. Those are vectors. But mass doesn't. Mass is just an intrinsic property of the thing that I'm talking about. This transformer might weigh 75 grams. I weigh 90 kilograms. I have 90 kilograms of mass in me. The transformer has 0.075 kilograms of mass in it, 75 grams. So if this doesn't have a direction and this does have a direction, the way our equal sign works is that the directions have to be identical on both sides. So since the mass has no direction, the only direction on this side is in the force. So this fraction has the same direction as the force, and the acceleration is the same thing as that fraction. So accelerations and unbalanced forces, note unbalanced force, the unbalanced force and the acceleration always point in the exact same direction. They are the same thing, just scaled by the mass. The force is that many mass units smaller, and that gives you the acceleration. The acceleration, that many mass units larger, gives you the force. And so this law has some simple common sense applications. Since acceleration is directly proportional to force and inversely proportional to mass, if I keep the force constant, so I don't let that change, a larger mass yields a smaller accelerations. And to put that in a simple sentence, it's harder to throw a lead shot put than it is to throw a baseball. I'm going to throw it as hard as I can. I'm going to take these two objects. I'm going to throw them as hard as I can. So I've got my metal ball here as the shot put, and I'm going to shove it away from me as hard as I can, exerting the maximum amount of muscular force that my arm can give. And when I do that, maybe I'll be able to throw it 30 feet. It'll land on the ground 30 feet away from me. It'll leave my hand, it'll accelerate until the moment it leaves my hand, and then there's no force pushing on it anymore. So from that point, it's going to continue sailing along horizontally at a constant speed. Newton's first law. And so with a certain amount of force that my arm can generate, a maximum amount of force that my arm can generate, the heavier shot put is going to leave my hand at a slower velocity than, with less acceleration overall, than the baseball will. A professionally trained athlete can throw a baseball hundreds of yards. A professionally trained athlete can only throw a shot put less. I don't know what the world record for a shot put throw is, but it's much less than a baseball. And then the flip side is here we considered equal forces. One person throwing an object as hard as they can, the larger mass object is going to leave their hand slower and fall to the ground sooner. They're not going to be able to throw it as far or as fast. If I switch it around and keep the object identical, so I don't let the mass change, but let the force change in the two scenarios, for the same mass, a larger force yields a larger acceleration. And so, in real-world language, a Major League Baseball pitcher can throw a baseball faster and further than a child, say, in a Little League game can. The adult, professionally trained adult with years and years of physical training, maybe some steroids to enhance the muscles, can exert much more force when he throws the same baseball. And so with a greater force acting on the same mass, you're going to get a greater acceleration, a greater exit velocity when the ball leaves their hand, and it will fly faster and further than a child throwing the same object. So common sense. You could have answered these questions. Can you throw a shot put further than a baseball? No. Why not? Well, the shot put's heavier. How does that enter into it? Mass. Heaviness is mass. Mass goes inversely proportional to the acceleration. How far you can throw something is directly related to how fast you can throw something. If you can't accelerate it much, you can't throw it very fast. Something that's got a lot of mass, you cannot accelerate very efficiently. You can't throw it fast. Something with little mass, you can throw fast. And then, who can throw a baseball faster? Who can throw a baseball further? A Major League pitcher or a Little League pitcher? Well, clearly the Major League pitcher. It's common sense. So Newton's laws just encode our common sense. Our common sense is just the result of our own personal experiences and experiments and observations of nature. Things we learned from the first moments we were able to walk up through elementary school All these instinctive things that we learned about how things move in the real world when we push on them, when we pull on them. These are just instinctive learnings of Newton's laws of motion. So when you're solving problems or answering an essay question, just keep that in mind. What you write down needs to jive with your common sense, because Newton's laws are just formal physical statements of our everyday common sense. All right, so I just want to get through his third law for this section. And this will take us back to the accelerating, decelerating, and turning car. So Newton's third law of motion is his most famous law of motion. If I give you the first few words, you can probably complete the sentence yourself. For every action, there is an equal and opposite reaction. And so for every action, action is another word for saying application of a force. For every time a force is applied, there is always an equal but opposite reaction. Another force, a counterforce. What this law tells us, and what Newton realized, this was one of his most brilliant insights, is that forces are always interactions between two different things. And so forces are interactions between two things. We like to use the word systems. One system is acting on another system. The ball sitting on the table, the weight of the ball is pushing down on the table is pushing up on the ball. The table and the ball and the table are two different things, two different objects, two different systems. The ball's weight is pushing down on the table is generating a force upwards, a lifting force on the ball. And those two are equal and opposite. Equal in strength, so they can cancel each other to zero. Opposite in direction, so they do cancel each other to zero. And my ball just sits here motionless on the table. You can see my ball there with a white backdrop behind it. And from his first law, that ball is just going to sit there for eternity until something happens to change it. Someone pushes on it. A janitor moves it. An earthquake shakes the table. Some external force needs to set the ball in motion, because right now the forces are perfectly balanced and they're not going to change. So forces are interactions between two things, and that means that forces always come in pairs. If the ball is going to push down on the table, there's no other way around it. The table has to push up on the ball with equal strength in opposite direction. If object A pulls on object B, then object B must also pull on object A. This is demonstrated as I twirl my transformer in a circle. Let me make sure this is well plugged in. As I twirl my transformer in a circle here, you can see that my hand isn't motionless. That in order to make it run in a circle, I have to keep moving my hand basically in the opposite direction that it's currently moving. So when it's up here and the transformer is moving that direction, my hand is pulling it a little bit back this way. But when it's down here and the transformer is moving that direction, my hand has to be pulling it in the opposite direction. They're pulling on each other. The tension in the cable is acting like a spring. It's pulling from both ends. It's transmitting. My hand is pulling on the transformer is pulling on my hand. My hand makes the transformer move in a big circle. The transformer's pull on my hand makes my hand move in a small circle. And in that way, they both circle each other. And so if object A pulls on object B, then object B must also pull on object A with equal strength in the opposite direction. And this is really important for space travel, because if I ask a 6-year-old to explain to me how a rocket works, I'm very likely to get, and if I ask the 6-year-old to draw for me, how does a rocket work? Draw me a picture. How does a rocket work? They'll draw the ground. They'll draw maybe a cartoon rocket. And they'll say, well, the rocket burns the fuel and the exhaust comes flying out and the exhaust pushes off against the ground and that makes the rocket go up in the air. But rockets don't need the ground. Yes, when I'm about to launch a rocket and I go through the countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, lift off. When the rocket first ignites, yes, the ground is there. But 1 second later, the rocket has lifted up off the ground. And 10 seconds later, it's hundreds of feet off the ground. And a minute later, it's thousands of feet off the ground. It's not pushing off the ground anymore. And yet, for the first second, the first 10 seconds, the first minute, the first 20 minutes of the launch, the rocket continues to accelerate, to move forward faster and faster and faster. I don't need the ground to make a rocket work, because how a rocket works, they work in the vacuum of outer space, far from any solid surface. A rocket works because they push their exhaust gases backwards with great force. I'm burning extremely explosive rocket fuel inside the rocket motor here, and that builds up. The fuel burns, turns into hot vapors, hot gases. Those gases are in a closed container, so they build up tremendous pressure, except there's one exit out of that container. And so the tremendous pressure of the burning gases in the container shoves the exhaust gases out the only exit hole that they have. And so all the atoms in the explosive gas vapors and the exhaust vapors, every single atom in the exhaust vapor is being accelerated out the back. It comes out the back at high speed. It was in here at 0 speed relative to the rocket. Now it's flying out the back at high speed, so it got accelerated. The only way for it to be accelerated is if a force pushed on it. The force that's pushing on it is the force of pressure inside the rocket chamber, inside the combustion chamber. And so the pressure in the combustion chamber pushes the gas out at high speed. But Newton's third law, if the rocket, item A, is going to push on the exhaust, item B, with tremendous force in that direction, so that's the rocket pushing on exhaust, then the equal and opposite reaction must also take place. If the rocket is going to push the gas downwards with tremendous force, the exhaust is going to push the rocket upwards with tremendous force. The exhaust pushing on the rocket. So the rocket goes forward as it throws the exhaust gases out its back. And so rockets push their exhaust gases backwards with great force, so inevitably, inexorably, you cannot avoid this. The exhaust gases must push forward with equally great force on the rocket. Accelerations, though, are inversely proportional to masses. So they push on each other with the same force. This F is equal to that F, but this is a lightweight substance with low mass. So the force divided by a small mass number gives me a large acceleration for the exhaust. The rocket itself, particularly when it's still filled with fuel, has unburned fuel, still has a large mass. And so the same force divided by a big mass gives me a small acceleration upwards, whereas the exhaust, having light mass, gets a very large acceleration out the back, downwards when I'm launching it off from the surface of the Earth. So the exhaust is of low mass, so Newton's second law requires lots of exhaust to push my rocket forward, so I have to have lots of fuel to push my rocket forward. To launch the space shuttle into outer space, to launch a satellite into outer space, I need a huge, tall rocket that is mostly a gigantic fuel tank, a 5-story fuel tank, 30 feet in diameter, to give me enough fuel, to give me enough exhaust to throw out the back to accelerate me up to high speeds, enough to break free of the Earth's gravity. So there's Newton's third law. Again, Newton, upon realizing and writing down his third law and recognizing, thinking through the implications of it, he realized that when a small body appears to be in orbit around a larger body, out in outer space, both bodies have to have orbital motion. Because the third law says that if the Earth, let's take the Earth and the Moon as an example. If the Earth's gravity is pulling on the Moon with a certain amount of strength to make the Moon orbit the Earth, then the Moon's gravity must be pulling on the Earth, equal and opposite. The Earth is object A, the Moon is object B. A pulls on B, but then that means B pulls on A. They pull on each other. It's a wording to remember whenever you're talking about forces. Two things push on each other. Two things pull on each other. There's no such thing as me pushing you. If I push you, you push back. If we're both on roller skates, I can't shove you away from me without me rolling backwards too. We're going to both push on each other. That's Newton's third law. Scientists have been experimenting with Newton's third law for 4 centuries, and we have never found any counterexamples to this. Forces always come in action-reaction pairs. I've got object A, I've got object B. Whether they're pushing on each other or pulling on each other, they do it mutually. A pulls on B, B pulls back on A in the opposite direction with the same strength. So Newton thought about orbiting objects, the Moon orbiting the Earth, Jupiter orbiting the Sun. The smaller body in each of those scenarios appears to be moving in a big orbit around the larger thing, but in actuality, both things have to be moving. They're in frictionless outer space. There's nothing to balance those forces. My ball is sitting here motionless on the table. The Earth's gravity is pulling the ball downwards. The counterforce to that is the ball's gravity is pulling the Earth upwards. The ball is a very tiny mass. It doesn't have a very strong pull of gravity. The Earth's motion in response to that is microscopically small, infinitesimally small, immeasurably small. As a result of the Earth's gravitational pull downwards on the ball, where the point of contact where the ball is touching the table, the ball is exerting its weight downwards, a push downwards on the table. And so the table must exert a push upwards on the ball, equal and opposite. So there's 2 sets of action-reaction pairs. There's the Earth's gravity pulling down on the ball, and the ball's gravity pulling up on the Earth. There's the ball's weight pushing down on the table, and the table's normal force pushing back up on the ball. And then the table is sitting on the floor, which is part of the Earth, and so the table's weight is pushing down on the floor is pushing back up on the table's gravity is pulling down on the Earth, or pulling up on the Earth's gravity is pulling down on the table, and these things just keep forming sets and systems where certain things pair up. The counterforce from one object is equal to the weight of another object. But everywhere in that description, I can find pairs of forces that are acting on each other. And so, out in outer space, though, there are no tables. So, if this is the Moon floating in outer space, and my head is the Earth floating in outer space, not connected to anything, the Earth's gravity is going to pull on the moon. The moon is moving sideways. The Earth's gravity pulls on it. It turns it. And so the moon moves in an orbit around my head. But at the same time, the third law demands that the moon's gravity is going to be pulling on the Earth. So there's an unbalanced force on the Earth. If there's an unbalanced force, there must be an acceleration on the Earth. If there's an acceleration on the Earth, and the Earth is in frictionless, empty outer space, it's not touching anything like a table to give it anything to resist or balance the moon's gravity, it must move in response to the moon's gravity. So it's incorrect to say that the moon orbits the Earth. Technically, the moon and the Earth orbit each other. The larger mass, in this case the Earth, must feel the same unbalanced force that it's exerting on the small body. That's a consequence of Newton's third law. So it must move. There's an unbalanced force present. It must accelerate. That's the first law. But my two bodies are not equal in mass. I've got a large mass object, the Earth. I've got a smaller mass object, the moon. The larger mass object will accelerate less because of its larger mass. The acceleration is directly proportional to the force. The two forces are equal, but it's inversely proportional to the mass. Earth's mass is larger, so the acceleration is smaller in the case of the Earth than it is in the moon. So the larger body is going to move. It's going to move in a smaller, slower, but otherwise identically shaped elliptical orbit. So the moon has a slightly elliptical orbit around the Earth, counterclockwise around the Earth, once every 27.3 days. The Earth itself, the head of my head, moves in an identically shaped orbit that's just smaller and slower and keeps itself synchronized with the moon's orbit. So both bodies are in orbit. They each have an orbit. And they're orbiting an imaginary motionless point that we call their center of mass. So earlier, I gave you, when we were talking about eclipses, I gave you this two-scale drawing of the moon's orbit around the Earth. And we kind of ignored this little inset when we talked about that. So here's the moon's orbit around the Earth. Follow along on your printout. The center of the moon's orbit is at the crosshairs of the major axis and the minor axis. The moon's orbit around the Earth is an ellipse, so it has two focal points on opposite sides of the center of the ellipse. And to most measurements, to the crudest measurements, it looks like the Earth is at one focus of the moon's orbital ellipse. But when we make really highly detailed measurements of the moon's motion against the background stars and the Earth's counter motion, we find that the Earth actually is moving. So this gray disk here represents the diameter of the Earth. Everything in my diagram is to scale. If this is the diameter of the moon's orbit, the Earth is 60 times smaller than the diameter of the moon's orbit. We can line up 30 Earths along the radius of the moon's orbit. And so if I zoom in here, I can see that the center of the Earth, the center of the gray disk, is moving in its own little elliptical orbit. This little elliptical orbit is the exact same shape as the moon's elliptical orbit. It's just a mirror image of it. The focus of the moon's orbit is to the left of the center. The focus of the Earth's orbit is to the right of the center of its orbit. And what they share at their common focus points, this is the focus of the moon's orbit, it's the focus of the Earth's orbit, that point is what we call the center of mass of the Earth-Moon orbital system. And what we see is that the diameter of the Earth's orbit is smaller than the diameter of the Earth itself. So while the moon is orbiting the Earth, I'm going to go grab my little models. Here we go. Standard Earth globe, 12 inches in diameter. A 2-scale moon globe, 4 inches in diameter, so that it's 3 inches in diameter, so that there are 4 moons would line up across the diameter of the Earth. As the moon there is executing this one large orbit, the center of the Earth is executing this much smaller orbit, and the orbit of the center of the Earth is smaller than the Earth itself. So while the moon is circling around the Earth, and to put this to scale, I have to take my, let's focus back on me. In order to get this to scale, I have to separate these two by 30 feet. So my moon has to be at the back side of the room, back side of the lecture room, while the Earth is at the front. But while the moon is circling around the Earth itself, if you look at it from above, is orbiting like this. It takes 27 days to make a tiny orbit like this, where the diameter of the orbit is smaller than the diameter of the Earth. So the Earth just looks like it's kind of wobbling around a point that's inside the Earth, but not at the center of the Earth. The Earth orbits here, a point that's about 3/4 of the way out from the center, only 1/4 of the way into the center of the Earth. And it takes 27 days to make that orbit, in the same amount of time it takes the moon 27 days to make this orbit. So the Earth spinning in 24 hours means this point is always moving. It's an imaginary point. It's inside the Earth, but it isn't physically attached to any part of the Earth. It's not always underneath North America or always underneath Africa. Africa, the Philippines, Asia, North America, Central America, they all get turned above that point. This point is just always directly below the feet of someone who's seeing the moon directly overhead, where they are right now. But Newton realized this, that because of the consequence of his third law, things in outer space orbit each other, and the point that they orbit is their center of mass. The center of mass is imaginary. There's nothing physically located there in space. It can be out in empty space between two bodies. If this were Pluto's moon Charon and Pluto, the center of mass would be just an empty place, a point in empty space out here in between the two bodies, in the empty space between the two bodies. They would both orbit that single point. And that point would orbit the sun. So, because the Earth has 81 times more mass than the moon, the Earth has 81 times more inertia. Inertia is a numerical value that we give to your resistance to moving, and it's directly proportional to your mass. If the Earth has 81 times more mass than the moon, it's harder to make the Earth move. It's 81 times harder to make the Earth move than it is to make the moon move. So they're pulling on each other equally strong. Earth's gravity on the moon, moon's gravity on Earth, they're equal pulls in opposite directions. And so the result is that the Earth's orbit is the exact same shape as the moon's orbit. It's just the Earth's orbit is 81 times smaller than the moon's orbit. And the Earth, the center of the Earth, in completing this orbit, at every point, it's moving 81 times slower than the moon is currently moving in its orbit. And in that way, they always stay on opposite sides. I currently have the moon here on the far right side of its orbit. That means the center of the Earth is going to be here on the far left-hand side of its orbit. When the moon orbits up to here at the top, the center of the Earth will be there at the bottom. When the center of the Earth is here on the right, the moon will be over here on the left. They're just always on opposite sides of their center of mass. So they both orbit their common center of mass with the same orbital period of 27.3 days. And because Earth's motion is so slow, it appears to be stationary. The moon orbits the Earth at 2,300 miles per hour. I divide that by 81, and I find that the Earth orbits at 28 miles per hour in its orbit. 30 miles per hour. I mean, a good racehorse can outrun the Earth's orbital motion due to the moon, and the whole Earth is shifting by less than its own diameter, so it's really, really, really hard to detect these motions. But we have. Radio astronomy demands it. 2 years ago, we produced our first ever picture of a black hole. In order to produce that picture, we had to link together radio telescopes all over the Western Hemisphere. California, West Virginia, Puerto Rico, Central Mexico, Southern Chile, Antarctica, the Virgin Islands, the Canary Islands, Hawaii. All these radio telescopes were pointed at the black hole at the same time while the Earth was turning, while the Earth is orbiting due to the motion of the moon. And you have to account for all those motions in order to combine the data to derive that really, 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 really high resolution image of a black hole that we produced. And so in making our radio telescopes work as one across the entire globe of the Earth, we have had to account for this orbital motion of the Earth. And sure enough, it follows the predictions of Newton's laws to a T. And everything I've said here, everything on this diagram that talks about the Earth and the moon, I can substitute the sun for the Earth and any other planet for the moon. So the sun and the Earth orbiting each other. The sun has an orbit due to the Earth's gravity. But the sun also has an orbit due to Jupiter's gravity. The sun also has an orbit due to Saturn's gravity. The 8 planets, the 8 major planets, are tugging on the sun in different directions at different times with different strengths. And the sun is responding to all of those forces. Add them together, sometimes they cancel. Sometimes Saturn is on that side, Jupiter is on that side, and Saturn's weaker pull of gravity cancels most of Jupiter's pull of gravity. And so the sun responds to Jupiter's gravity less than at times when Saturn and Jupiter are in the same direction as seen from the sun. And so this figure here shows a scale diagram of the sun. So this yellow disk is the sun, and this loop-the-loop path starts at 1945, 1946, 1947, 1948, 1949, 1950. Each of the little white dots is the position of the center of the sun a year later from the earlier dot, and it's carefully diagramming how the sun is moving over the 20th century, the second half of the 20th century, due to the combined gravitational pulls of all the planets. And in particular, the sun has a 12-year loop that's due to, because let's just start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got this loop here, that's Jupiter's gravity, and then a bigger loop, which will be a 30-year loop. So if I start, and let's start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Roughly a 30-year loop. That bigger loop is Saturn's gravitational pull on the sun. And so you just have to combine all of them together. If the sun is moving this way, then Jupiter must be down here moving that way. When the sun is moving that way, Jupiter must be up here moving this way. When the sun is here moving upwards in that direction, Saturn must be over here moving downwards in that direction. And when the sun is over here moving downwards in that direction, Saturn must be over there moving upwards in that direction. And then the weaker poles of the smaller planets, Mercury, Venus, Earth, Mars, are just almost imperceptible wobbles compared to the strong gravitational poles of the larger planets. And so the center of mass of the solar system, considering the current mass and location of the sun, the current mass and location of Jupiter, the current mass and location of Saturn, The center of mass of the solar system is just some fixed point that stays near the sun stays near that fixed point, but orbits around it due to the changing orbital locations of all 8 of the planets. So I'm going to summarize Newton's 3 laws of motion, and then we'll end this little section. Newton's first law of motion: an object moves in a straight line at constant velocity, or it remains motionless until acted on by an unbalanced force. The key highlighted, italicized word there is unbalanced force. My globe is sitting here motionless. My moon is sitting here motionless. My little steel ball is sitting there motionless. There are forces acting on them. Gravity is acting on them. The table is balancing gravity. Molecules of air are hitting this side of the steel ball, but molecules of air are hitting that side of the steel ball, so those two are balanced. Molecules of air, the front and back, are balanced. Everything's balanced. There are no unbalanced forces acting on the ball, so it's not moving. It remains motionless. However, if I unbalance the forces by applying a force from one side without a counterbalancing force to the other side of the ball starts moving and continues to move in a straight line until disturbed by something else. This is what makes a billiard table, a pool table, is a perfect example of all 3 of Newton's laws, because the only way you can become an expert at pool is learning that, well, if I hit the ball at this angle, it's going to move off at that angle in a straight line until it hits the walls of the pool table or it hits another ball. It's predictable because things move in straight lines unless a force is acting on them. A well-maintained pool table is perfectly level. The felt is nice and smooth with no bumps or ripples or tears, no unevenness to it. So my pool balls just roll in straight lines until they hit the sides of the table and ricochet off, or they hit another ball and ricochet off. Newton's second law, the acceleration of, if a mass is changing its motion, it's being accelerated. That acceleration is directly proportional to the unbalanced force that's pushing on it and inversely proportional to the mass. You want something to move more, push harder. If you have a fixed push, a lower mass thing will move more. Common sense. Harder to throw a shot put than a baseball. A major league pitcher can throw a baseball further and faster than a little league pitcher can. And a little league pitcher, a teenager, can throw a baseball further and faster than a Pee Wee League 4-year-old can. They have stronger arms, more musculature, they can apply a larger unbalanced force to the baseball, accelerating it more. And then his third law is this famous one: for every action, there is always an equal but opposite reaction, emphasizing the always. Every single system in the universe, every pair of objects in the universe, whenever any force is exerted, there's always two things. One object is exerting a force on another object, but that means the second object is exerting the same force on the first object. They're just pushing in opposite directions, or pulling in opposite directions, or pushing in opposite directions with equal forces. My rocket pushes exhaust gas out the back with a strong force, and so the exhaust gases apply the exact same strong force on the rocket itself, pushing it forwards as they get pushed backwards. There's no way around that. It has to happen. And in 4 centuries of doing all sorts of experiments, we've never found an isolated single force. It's always a force-counterforce pair. But as I can demonstrate here, if I consider my body one object and the transformer another object, I can make the transformer move dramatically, whereas I don't appear to move at all because, yes, the transformer is pulling on me, and that should make me want to move, but my feet are firmly rooted to the ground through the force of friction, through the soles of my shoes. So whereas the transformer dangling from the end of the cord out in open air has nothing to help it apply a balancing force, a counter force is not the same thing as a balancing force. The tension in my cord is pulling on my transformer, accelerating it, making it turn, making it move in the circle above my head. The tension is also pulling on my hand, and you can see my hand moving a little bit, but my hand is connected to my arm is connected to my body through my feet are connected to the floor. So as strongly as the cord is pulling me sideways, there's a balancing force from the floor that's helping me resist that motion. And so my body doesn't move much because it's touching something else. The transformer isn't touching anything but air, and the still air in this room just can't provide a balancing force to counter the pull of the cable, and so it has to move. The pull of the cable is an unbalanced force. The pull of the cable on the transformer is an unbalanced force, so the transformer moves. The transformer's pull on me, transmitted by the cable, is balanced through a force with my shoes on the floor. So I don't move so much. Out in outer space, there's no contact points. There's nothing to touch. Outer space is a vacuum. It's frictionless. So the moon's gravity pulls on the Earth. The Earth has to move. There's nothing, no contact point, no support point, no table, no floor for the Earth to have a balancing force to balance the moon's gravity. The moon's gravity on the Earth is unbalanced. The Earth moves. The Earth's gravity on the moon is unbalanced. The moon moves. They move around each other. Try and do this. They orbit each other, and as the pay attention to me, the video is tracking this little lanyard around my head, so when I block it, the camera decides to drift off. But they're moving each other. As the moon orbits in a large orbit around the Earth will wobble in a small orbit that's just always opposite the moon's orbit. It's 81 times more massive than the moon, so its orbit is 81 times smaller and 81 times slower compared to the moon's orbit. So it's almost unnoticeable unless you have really, really, really high precision astronomy equipment. Same is true for the sun's motion. The sun's orbital motion due to all the planets is about 1 meter per second, which means walking speed. This is how fast the sun orbits around the center of mass of the solar system. Just a walking pace like this. So it's incredibly slow, hard to detect from 150 million kilometers away, 93 million miles away, trying to tell that something is moving at a mile per hour when you're 93 million miles away from it. It's really hard to detect. But again, radio astronomers have been able to do so. And so, by combining these three simple rules with his mathematics of calculus, Newton was able to show that all forms of heavenly motion, the moon orbiting the Earth, Jupiter's moons orbiting Jupiter, all of the 6 known planets orbiting the sun, they were all predictable, understandable, calculable, predictable, and all forms of earthly motion as well. I shoot a cannon out of a cannon, I shoot a cannonball out of a cannon, I can predict, just given the angle and the exit speed, I can predict where it's going to land. Wind blowing on a ship sails. Given the size of the speed of the wind, the size of the sails, the mass of the ship, I can predict how fast it's going to move. All of these things became understandable, calculable, and thus predictable as a result of Newton giving us these 3 laws of motion. All right, I'm going to end this part of the lecture here. So we've covered definitions pertaining to motion and Newton's 3 laws of motion. These are covered in the last section of chapter 3 in the textbook.